let's get started. Oh no, we're going to let everybody that's talking get started first. So I'm not important. All right. You know, you guys ran out of time on the test Wednesday. You needed more time. So when I ask you, you gotta, when I say, all right, let's get going, that's a sign. Zip. All right. Goes for everybody in here. All right. Even the TAs. All right. What we're going to do is for the first part of class today, we're going to hand back printouts in alphabetic order, and I'm going to practice your names as I do that. And if you haven't had a Scantron printout, I'll explain how they work. They're pretty basic. But let's get down to the. So we just got these back from it. This is it? What the? That can't be right. Did you look at this?
I didn't even open it now.
This can't be right. Okay. Hold on a second. Okay, this is the top. What is that? No, what is this? That's the middle of the alphabet.
Just put them out of order.
Yeah. What's the next one? Is it an E? What is that?
4 of the second.
What's the one after that?
Looks like there's 4 of everything.
Oh, you know what that is? They forgot to fill in their test form. All right.
Oh, these are the ones that didn't fill in.
Yeah, that's these people here. Yeah, Isabel. See, now this is a problem because I have to go back and look up.
Do it by hand?
No, I have to go dig it out of the pile, and the pile's not. All right. Before we hand out exams, I want the following individuals to come up here. Isabel Gutierrez. You're in trouble. Not really, but come on up here. Isabel. Nalisha Torres Mangual. Also kind of in trouble. Melanie Del Toro. Benjamin Mans. Step forward, Earthling. And Kara Solomon. Yeah, you're all on the bad. You're on my bad list for the next 40 days and 40 nights. Okay, come on over here. Come right over here. I'm going to turn off the. Oops, your names are all recorded in YouTube. Okay, we're back on. Okay, let's get going. Let's get going with lecture now. Now, we just finished handing back printouts. In case you haven't gone over one of these before, I want to point out a couple features of it. Let me blow this one up a little bit. Of course, it has 1 through 30, and it indicates which one you got wrong. And it also has the key over there, all right? And so you can see what the correct answer is. Now, this in itself is not that helpful, but what I'm going to do is publish a PDF, a little in PDF form, a little blurb sheet to give you the gist of each question, except for the matching items at the start. And so you'll be able to look at this and then look at the blurb sheet and say, ooh, it looks like I missed a lot of voltage questions, or maybe some other pattern. And then for the final, you'll be able to, and probably for exam 2, it's a good thing to study up on it as well. Because I mean, we're not gonna be finished talking about voltage until Christmas, until Thanksgiving. Um, so anyways, so I'll be doing that in the next week or so, and I'll publish it in web courses. And it makes a nice little study, kind of a mini study guide. All right. Now the blurb sheets that I give you um, are not going to be verbatim of the questions that you had on the test. All right. But they'll be enough so that you'll be able to maybe remember the question or at least know the general topic. And because the chances are very low that I'll actually reuse any of those questions from exam 1 on the final. Although some of them might be a little bit reminiscent of things you see on exam 1. Question, Mr. Legister. Yeah, for each of the 3 midterms. Okay. And so I can't believe how fast this is with you guys. I'm used to classes of about 300 students in the big subterranean lecture hall downstairs and across campus. And any back exam printouts is a chore. But this is good. Okay, so that's the big stack of questions in there. Your name is on there, your UCF ID, the form number. Now the form number, I don't know what that is. That's the number you are in the stack of Scantrons, I guess. And it has the version up there. Now, over here, I want you to point out something. Now, this is an astronomy exam from a student, John Q. student, a few semesters ago. You see that percentage score over there in the upper right. I want you to just kind of mentally cross that out because that doesn't know anything about clicking. So do not deceive yourself about what that percentage means. It means precisely jack in terms of your exam score, because this doesn't have the clicking points that you may have scored from clicking. All right. So, but definitely pay attention to the raw score. Raw score and total points are the same for my tests. And so what that means is that you now have a portion of your something out of 42 for exam 1. Okay. Now I'm in the middle of grading the iClicker questions, and I'm going to have to pull them apart so that I can give a little bit more partial credit on those. So hopefully I'll have that done. But these data, your raw scores are now in web courses, and they're in there. You may have noticed it shows up on your grades page as being muted or something. But I'll unmute that and you'll be able to see it there. But you got your printout now, so that's good. All right. Now I want to. I'll ask for questions in just a second, but I want you to double check your printout for double answers, which are going to be marked wrong, and also for blanks. And then if you have one of those, so take a look at your printout. Okay, if you have a printout, and see if you got any double answers, and because they'll be marked, because there was no item on the test that had 2 acceptable answers, or that 2 different dots were required for the answer. So anybody have a double? 1. Anybody have a blank? Okay. Those of you with blanks and doubles, come back up here and give me your printout back. And what I'll do is I'll actually look through the Scantrons. Okay. Doubles and blanks, come on up here. No, you don't have to. It's easy to see. All right. Andrew, I'm going to Is there any staples in this stapler? Staple melodies. All right, now you're not going to be able to do anything with melodies, but actually you will. Take that back. Um, now, what I want you to do is take this set of scan. Go down to the lab so you can spread out. Okay. And just look. Oh my goodness. So, for those of you that have blanks, it may be that you didn't darken them in dark enough. Okay, so we'll check for that. So if they have a blank, see if it's actually darkened in it, just kind of faint. And then mark it +1 if it's correct. Okay, so if she has a C here and it's just not too dark, give her a +1. Otherwise, say no change. And do that for all of them. And if somebody has a double answer, like here, see which one's erased and which one's not. And then if B is not erased, give them a +1. Otherwise, all right. So go get somewhere quiet and do that. Spread out and stuff. Okay, let's get back to business. You're doing it again. Thomas. My name is Thomas also. And I'm ready to discuss things. All right, so do you have any other questions about your printout? Robert. Andrew. Close. That was on the clicking. The bonus question was on the clicking section. Okay, so all 30 of these were regular points. Oh my God, did you bubble in multiple? Did you have 34 dots on your Scantron? Yeah, they were multiple choice with the iClicker. So all you have to do is type in the letter, and then you send it. And for the so the first 3 or 4 I think were multiple choice, and then you send them in, and those and so you can actually get 13 points on the iClicker portion. It's supposed to be 12 regular, and then 1 bonus, and the bonus point was the multiple choicer. All right, so that's in the iClicker data. All right, another question. What? You're kidding me. That can't be right. No, you're thinking the one that says bonus point is on the clicking page, right before the calculations. Right, so you don't have it right in front of you, but that's the way. This is the clicking page. And here's the instructions up here, and then here's the first 3. This third one was multiple choice bonus, and then there were 4 calculations to do. And then the previous page was multiple choice for the Scantrons. This is Form B, I think. No, this is Form A. C? Yeah, I'll think about it. I don't have them with me, but I'll do that. I'll double check it for paranoia's sake. Another question. Wait a minute. Heidi. Yeah, go ahead. Are we going to go over the clicker questions? Funny you should ask. The answer to that is yes. We're going to go over the calculations right now. So you might want to take some notes because I looked at the data, and the reason that they're not posted, usually the clicker data is posted very quickly before the Scantrons, but the Scantrons came in really fast this time. We turned them in at about 1 o'clock Wednesday, and they were out by about 3 o'clock. Sometimes it takes 2 or 3 days, so you just never know. The reason that I'm taking time with the iClicker questions is because I want to dig out partial credit because there was a lot of difficulty with the calculations. So take some notes. Let's go through some of the questions. And actually, all the clicker questions were about this diagram. And one of the brain burner was actually the optional bonus question. The direction of the equipotential line, that was number 3. And then the other brain burner was the direction of the total electrostatic field at point P. So that's out here, way out in the upper northeast quadrant. And here's the basic answer to that. It's a brain burner unless you think visually. The electric field from the proton is going to point basically northeast. If you're out here, you're going to be pushed away from, if you're a positive test charge, you're going to be pushed away. So your field vector from the proton is northeast. Now, the electron is going to draw you back southeast, roughly. The opposite direction, the opposite quadrant. It's going to be down and to the left. All right? But the electron is so far away, it's going to have a much smaller force. All right? And therefore, you're going to have a lot of northeast and a little bit of southeast, so the net is northeast on that one. And figuring out the exact direction, that would be a real bearcat. But you could do it. I mean, if we had a 2-hour test, you'd have to do trig out the wazoo for that. The electric field at point M, let's see, calculate the electric field at point M due to the proton and electron. Oh my goodness. Which part of the calculation is actually the same? And it's the part of the calculation that's the same, and we'll see that in a second, is the numerator, K times E. One of them's got a minus sign in there, but now the brain burner was about this point here, H, the optional one. What's the direction of the equipotential line? And because the electric field at that point, which is number 4, that's like a nearest neighbor's problem. So it's dominated, the electric field is dominated by the proton, so it's going to be rightward at point H. And that, for that reason, since the electric field is straight to the right, the equipotential line is going to be straight up and down, north-south in this one. So you had to actually do think about number 4 in order to get that bonus point there. And hopefully you got that. All right. So we're going to calculate the field and the potential at point H. So the number 4 was calculate the size of the electrostatic potential at point H. Number 5, calculate the size of the electric field vector at point H. And then this was the bearcat. Figure out the size of the electric field vector at point M due to the proton and the electron. Now, this one's a little bit tricky because you're putting together two vectors and one of them is slanted. We're going to work through that with you. All right. And then number 7 was calculate the direction of the electric field. Now, here's the scoop, and we'll just do some verbal descriptions here. At point M, the electric field vector from the proton is straight up and down. Now that's closer. That source charge, the proton, is closer to point M. The electron's way far away, right? So you're going to get a lot of newtons per coulomb vertically from the proton. Now the electron's going to draw you back to the southeast again. But again, that's going to be, so it's going to be a little bit of southeastness, all right? But it's not going to be very big, as we'll see. And so that's going to tilt your arrow from your net arrow of the electric field from straight up, if it were just the proton, to a little bit shorter and a little bit tilted into the northwest quadrant, because we're going to have a little bit of drawback from the electron to the left. Right? We'll see. We're going to build that up. So let's start building it up right now. Right now, we're not going to mess around too much with point H, but and here's the electric field at point H. We'll calculate that in a second. Those are the cinchy ones. This one's the Bearcat, and let's get it set up. First of all, sketch in your radius segments. The radial distance from the proton to the field point is A, and then the other one's on the slant. So that's this red dotted line segment from the electron over to field point M. And that one's a little bit bigger. You do your Pythagorean theorem, 2a quantity squared plus a squared. That's a total of 5a squared. Square root that, and you get a distance of square root of 5 times a. So it's about 2.23 times a. Now we're not going to put in 2.23. We're just going to leave it as square root of 5 for now. All right. Now, if here, I drew a nice big electric field vector from the proton, E subscript P. Now it's straight up, as it should be. And the other one is going to be down in the direction of that slanted hypotenuse. The two source charges and the field point form a triangle. Okay, the hypotenuse of it is that red dashed line, and that's the direction of the electric field from the electron. However, I want to make a point. The square of the distances is 5 to 1. So the square of the electron distance over the square of the proton distance is 5 to 1. All right? 5a squared over a squared. Okay, so 5 to 1. Right? And what that means is the sizes of the two electric field vectors are going to be 5 to 1. The proton is going to be 5. The field from the proton is going to be 5 times bigger. All right? Now, the reason I'm showing you this is so that you can get a feel for, like when you're sketching this, all right, how big do I make that second vector? I mean, we haven't got it sketched in yet. We know the direction roughly, but is it going to be the same size as E subscript P? No, it is not. It's going to be a fifth of the size. So sketching a shrimpy vector, and this one is exactly 1/5 the size. There's the electric field pointing back towards the electron, as the electric field should for a single point charge. Now the total electric field is the vector sum of those two. So we have to draw a parallelogram. And so here's the blue dashed line. So there's my parallelogram. And then from point M to the other corner of the parallelogram, whoops, I just greased it all. Let's go through this again. I hit the up arrow instead of the down arrow. Okay, so there's that. Now here's the parallelogram. All right. And there's my total electric field vector. Now that's graphical. You didn't have to do that. But you know what, you guys? I always, when I'm working on a problem, I always start with diagrams and pictures. I'm always trying to think about that. And this one, I I took like an hour and a half to make this one diagram, and so I could make sure it was exactamente on the money. Now, you don't have to be Leonardo da Vinci Jr. on your sketches, because you're going to let the numbers do the talking anyways in the end. But hopefully it would look a little bit like this. All right. A little bit of southeast, maybe a little bit shorter, a little bit longer than what I've got, and a big vector going straight north. And then your total vector being a little bit shorter than the protons field and tilted a little bit into the northwest quadrant like that. All right. And remember, we're going to let the numbers do the talking. And how do we do that? Well, I want to draw your attention to this little teeny tiny sliver of a triangle right up here. See this one? That little purpley guy? All right, now that's the same up there as this one down here. All right, and that's the one for the to figure out the components of the electron's electric field. So let me push this over here and magnify it a little bit, 4 times. All right, so then this is the triangle. So this is the triangle that is going to give us the components of the electron's contribution on the slant. You know, we're going to be on that hypotenuse, right? This is a blow up of it. And we've got to do some trig. We got to get sines and cosines. And I always like to draw a little right triangle, you know, nice and big, try to make it the same proportions, off to the side so I could think geometrically and trigonometrically in 3 dimensions. All right, so really, here are the cosines and sines of that triangle, the one that's going to give us the components of the electron's field, the small red vector. All right, so there's the setup for all 4 calculations. Now let's get down to the nitty gritty. With the electrostatic potential at point H. All right, now we're just going to grind out the formulas. We've got a sketch for all this stuff. Now we're just going to grind through the formulas, see if we can make them make sense. This is the easiest part of using voltage. You're always just adding up whatever the point charge potential is. You don't have to worry about trig on this stuff. All right, with electric field, yes, but not with this. It's got all the trig built into it, but it's a scalar function, and you just add them up. So the potential at point H due to the electron plus the potential at point H due to the proton, easy as walking in the park. All right, so K times minus E on top over 4A. Yeah, 4A is the distance from the electron out to my field point H. All right. And my field point H is 2A away from the proton. So that's KE in the numerator and 2A in the denominator. Now there's another common factor, K times E. All right. And we need it for the potential, and we also need it for the electric field. So, you know. Now let's deal with these fractions. 1/4. Let's factor a 1/4 out, negative 1/4, and a 1/2. And there's my KE over A. And out front, I've got a negative 1/4 plus a 1/2. So that's equal to positive 1/4 in the square brackets. All right. Agree with me? Yeah. All right. So a little 7th grade fraction activity there. So there's the 1/4, and then here's the numerator. Now, 9 times 1.602 is 14.418, and then when you put in the powers of 10, 9 times 10 to the 9, 1.602 times 10 to the minus 19, you get 1.4418 times 10 to the minus 9. Anybody remember getting that in your calculations? Your brain may be so fried that you don't remember that, but that's what it is. Okay. Now, I'm emphasizing this so that you can remember to use that as a tactic. You calculate it once and do it right, and just realize it shows up several times. You don't have to recalculate. Do it once here, and then just rewrite it in the next time you need it. K and an E together. Now down in the bottom, there's a factor 4 down there, and then the value of A, which is 1.25 times 10 to the minus 9 meters. All right, and you can see that the numerator. All right, thanks. Did anybody have a change in their grade? Okay. You guys that handed me in your blanks and stuff and your doubles, no change in your grade. So that means the blanks were true blanks, not faintly dotted in, and the doubles were wrong. The one person with a double had a wrong answer. All right, so that's good. All right, so so now you just got to calculate this out on your calculator, and notice that above there, the numerator is 1.4418, the denominator is 1.25, so that's a little bit bigger than 1, right? And then there's 10 to the minus 9 on top, 10 to the minus 9 on the bottom, so they cancel out. Nice. All right, so I've got a little bit bigger than 1, and then I've got the 1/4 out in front. So it's going to be a little bit bigger than 0.25. And when you actually calculate it out, it comes out to 0.028836 volts. Now, I asked you for the nearest 0.01 volts. It's positive, and 0.29 is what you should have clicked in. Question? Emma, question? Okay. All right, so that's the voltage calculation. Anybody have a question? All right, let's keep going. The electric field. All right, now we know it's to the right, so I parked a little vector over there because I know that's basically what I've got. Now, it's KE over R squared in general. So the proton's field is KE over 2A quantity squared, because the distance from the proton out to the field point H is 2A. And then the distance from the electron out to the field point is 4A, so it's KE over 4A quantity squared. All right. And then that's the magnitude of the electric field. And then the electron is going to give some leftward. So it's going to look like this. There's going to be some rightward. So look down there at the very bottom. There's the field from the proton. And then here's the leftward field from the electron. All right. So and those are measured out carefully. All right. Now let's do the actual nitty gritty. And this is what I'm going to do. I'm going to do KE over A squared, because I've got, if you look at both field magnitudes for the electron and for the proton, I've got a KE and an A squared in the bottom, and then I got a 16 and a 4 in the bottom. So I could deal with that as fractions. All right, so KE A squared, I want to get that. So there's my numerator, 9 times 10 to the 9, Newton meter squared per Coulomb squared. 1.602 times 10 to the minus 19 coulombs for the charge of the proton. And then 1.25 times 10 to the minus 9 meters in the denominator, quantity squared. Now, that denominator squares out to 1.5625 times 10 to the minus 18 meters squared. All right? Because remember, when you square the stuff inside the parentheses, you got to square everything. So 10 to the minus 9 squared is 10 to the minus 18. 1.25 squared is 1.5625. And meter squared is square meters, right? Now the top we already talked about, 1.44 times 1.4418 times 10 to the minus 9. And notice that I'm carrying a few extra digits. My final answer, I want to have 3 significant figures, but I'm going to carry a few here for extra gravy until the very end. All right, now you can see that I'm going to have a 10 to the minus 9, but my numeric quotient, 1.4418 and 1.565, that's actually less than 1. So I might get about a 0.9 something or a 0.8 something times 10 to the minus 9. Okay, and so that's going to be 9 point something times 10 to the minus 8, or times 10 to the 8, right? And that's exactly what happens. So there's your quotient, and it's newtons per coulomb. Meters squared cancel. Okay. Now that's KE times A squared. Now to get both values, I've got to figure out 1/4 of that. And then over here, 1/16, and it's got to be negatory because it's leftward. All right. So here's the field strength from the proton. All right, and here's the vector for it. Again, it's a rightward vector to the right. And here's the field strength and the direction with the minus sign for the electron. And here's the little teeny vector for it. All right. And so if you add up those, calculate those two numbers and then add them together, you get 1.73 times 10 to the 8 newtons per coulomb. So your answer on that question is 1.73, and hit the send button. I didn't, I looked at your guys' work with the EE, using EE for scientific notation, and it's pretty much a disaster. So that's why I gave you give me the multiple of 10 to the 8th to 3 significant figures. And that's what it is, 1.73. And it's positive, so that means rightward. Questions? Okay, let's keep going. Let's get to the brain burner. Oh, and by the way, just so you know, when you're looking at this in YouTube, these vectors, these red arrows, they are correct. I made this vector right here is the key arrow for the entire set of problems. I made this one 100 pixels long. That means that this one is going to be 25 pixels long, and the net is down here is going to be 75 pixels long. And so that's the way it is on this diagram. And it carries over to the next one as well. This one is 400 pixels long for this big electric field from the proton. And then this little one down here is 80 pixels long, and it's tilted in the right direction. So I worked really hard to do that. All right, so here's my triangle. And again, I'm going to have to figure out KE over A squared here. And notice in this triangle, I've got my minus signs attached to the cosines and sine and cosine. All right, and that's to remind me that the electric field contribution from the electron is third quadrant, negative, negative. All right, now there's my triangle. Okay, that's what we're going to use. Let me pencil in the electric field vector. Here's a big version of the electron's electric fields. Okay, so that big red arrow now on the triangle, that's the one we got to figure out. The electric field of the electron over here, that's pretty cinchy. Just KE over A squared. We already know that. That's 9.22752 times 10 to the 8 newtons per coulomb. All right. That's 1.4418 times 10 to the minus 9 over 1.5625 times 10 to the minus 18, or 10 to the minus 19, no, 10 to the minus 18. And then there's your quotient. All right, that's the easy one. Now, the other one is going to be 1/5 of that size. All right, so the electron, remember, is 1/5 the size, the electric field from the electron. right? So I just got to, for the magnitude, I just got to park a 1/5 out there, Melanie. So my leading factor there is 1/5, and then my 9.22752 times 10 to the 8 newtons per coulomb. All right, now that's going to give me my hypotenuse. Once I get my hypotenuse, I'm golden, because then I just got to do some trig. And I already got the trig ratio set up there, plus or minus 2 over square root 5. All right, so, oops. Let's go back. There's the, okay. All right, here we go. So the electric field of the electron, magnitude-wise, is, and look at that. Those are about, if you multiply the electric field magnitude of the electron times 5, you get 9 point something, obviously. All right? Times 10 to the 8. So we're looking good magnitude-wise. Now we just got to apply the trig ratio. So that the cosine of theta, in this case, -2 over square root 5, third quadrant, works out to a negative 1.650665 times 10 to the 8 newtons per coulomb. Now that's the one that's going to tilt that net field a little bit into the northwest quadrant. All right. We know it graphically. We know that that's what happens. Now we know exactly how far over it goes. All right. Now the y component is -1 over square root 5 times the full magnitudes times the hypotenuse, 1.8445455 times 10 to the 8 newtons per coulomb. So that one works out to negative 8.2533 times 10 to the 7. Now that's 10 to the 7, so that's a little bit smaller. All right, it doesn't have a huge amount of newtons per coulomb compared to the proton's contribution. But, you know, it's enough, and we got to take care of it. That's the same as negative 0.82533 times 10 to the 8. So that's how we're going to add those together. All right. And so when you add those two together, the y component from the proton, the y component from the electron, you get 8.402 times 10 to the 8. All right. Now, we also have so that's the y component of my total vector E. And then this is the x component of the total vector E as well, because it's the only xness, it's the only horizontalness that comes out of the diagram. You know, I don't see a whole lot of you watching this diagram. I'm just whistling, I'm just narrating your life, man. If you don't look at these diagrams and these equations, God bless you. I spent hours getting this ready for you guys, because I know you crashed and burned on Wednesday. All right, so we got our components. Let's put them together now. All right. Now we know what the arrow looks like. I did this ahead of time, and then I made my calculations. And there's the calculation results. A little bit of leftness and a lot more of upness for the electric field, the total electric field. So let me park that over there. All right, now this is my triangle for the total electric field. All right, so let me park that over here to the right and do a little bit of trig. All right, and there's my components. 8, and I'm leaving off the 10 to the 8th because I don't need 10 to the 8th for figuring out the trig. 8.402 and 1.651. And I already, you know, and we can figure out the magnitude. That's just this Pythagorean theorem. And then, so there's the magnitude except for the factor of 10 to the 8th. So we'll tack that in at the very end. And let me do that up here in blue. So there's my magnitude, 8.563 times 10 to the 8th. So your answer this is the answer for number 6, 3 significant figures. So you're going to, you should type in 8.56 and hit the send key. Now, the other thing that you had to do is to figure out the tilt angle of that vector. And we know it's going to be northwest, so it's going to be somewhere between 90 degrees and 270. Or so, yeah, somewhere between 90 and 180, third quadrant. Now, the angle of the measure of the larger angle in the right triangle is 78.9 degrees. Okay, that means the other one is 11.1. All right, so let me bolt that out of here. That means that this one right here is 101.1. Those two, so 78.9 and 101.1 add up to 180. And so that's the answer for number 7. And that was a Bearcat as well. All right. Questions? Dude, this is all going to be on YouTube, so you don't have to make photographs of it. Although it's possible, I know. It's all going to be on YouTube. So it'll be recorded. Questions? Hold on a second. Emily. Yeah. See, I'm getting more names in the future. Yeah. Yeah, you're gonna, and I'm gonna adjust things for the next exam so that you have more time. Yeah, it's, yeah, yeah, yeah. It's, the thing is, yeah, you guys needed more time. The thing is, nothing in here is bodacious. It's, I mean, everybody's in here done trig and right triangles at the wazoo, and you've drawn sketches and whatnot, sines and cosines. But putting it all together is, it's, and you know what it reminds me of? That those, the second week of classes when we had that set of 3 or 4 protons and electrons in a row, equally spaced, and each thing you did there was kind of cinchy, but putting it all and getting the directions right and the sizes right and everything, and then adding them all up, that was a little bit and this is even more intricate. But so and I expect a lot. All right. And for those, and I've been thinking about this all since yesterday, and I'm trying to relate it, to the common thread in here seems to be med school and medical professions and stuff like that. If you're in a medical emergency and somebody's life is on the line and you don't know what the hell's wrong with them, you're going to wish it was this easy, because you're going to be under real pressure to get it right and save that life. My niece is a doctor. She's a neonatologist, so she's in the NICU all the time. Little tiny babies just fighting to live. And she loses some. And every time she cries. Every time. And you want to diminish that. So you want to be able to think carefully and quickly and with an intricate, and this is child's play compared to the human body. You got some little kid that's dying on you. Some mom of 4 kids and she's the sole breadwinner for the family and she's dying on you and you don't know what it is. What are you going to do? You got to be able to think and do it quickly and stuff. So you're not going to be doing trig in the hospital. Thank God for that. But you are going to have to make, put everything together quickly and rapidly. So I'm going to be giving you more time on exam 2. So this is kind of a test run to see how you guys do. And yeah, and I know that the grades are going to be a little below, but don't forget, we have 3 grades to, we have 1 exam to burn. And you know what? In most classes, even without a brain burner of this magnitude on the first test, for many students, exam one is the first one that is this is the one that gets dropped out of the three. So for some of you, now some of you guys did pretty good on the clicking or on the Scantron, I noticed. Now if you got 20 or more on the Scantron, that's good. Okay. Well, the Scantron was a little bit tough too, but now you know what my exams are like, and it's gonna be high demand. You will have more time next time, and you're gonna want to, Emily and everybody, you're gonna want to try to remember you got to work fast and well, and that's why paying attention when I go through it now. This is the post-mortem. This is why the patient died. So next time you see something like this, you won't have to work so it takes so long, and you'll keep the patient.
I think it was a combination of the clicker question before and then the break and then it was like.
Yeah, I know. I thought having the clicker questions would be helpful, which I think it was in a way. But you guys were also, in case you didn't figure out, I put that last clicker question in the mini review because I knew that this was coming up. And I wanted you to get your brains thinking about the trig and the components of stuff, but it just wasn't enough time. All right. Any other questions? Yeah.
For the next exam,
Pete.
will there actually be
Peter,
a study
right.
guide? Yeah.
Study guide?
Yeah, I didn't see one in discussions at all for the first one.
Well, look, Brandon does that out of the goodness of his heart. Apparently so don't get on him because of, I'm not saying you are, but don't get on Brandon if he doesn't come up with it. Because he's got his own obligations and he's doing that out of the goodness of his heart. And God bless him for doing that. Apparently his computer fried out, or the dog ate his computer or something the night before. But he wasn't able to get it. I was wondering, man, when is he gonna? I waited up to like 11 o'clock the night before to see what he's got because they're usually pretty good. All right, so let's give him another shot for the next one. But I do not ever give study guides. Your lecture notes are your study guide. That is why you take notes. And organizing them and stuff. And that's what Brandon does. I mean, he distills lecture notes and what he reads and stuff. All right. And I know, and most of you guys are not newbies to UCF, but the classes where I have a lot of freshmen, newbie freshmen stuff. Oh, Dr. B, are we going to have a study guide for the exam? And what they want is like the study guides they had in high school. And I've seen, my son went through high school here in Florida. And some of the study guides that I saw for his, and then compared to his exams, they're basically giving the exam away. And you're never going to see that from me. You're always going to be working your ass off on, working your you-know-what off on a test. You're not going to get any freebies out of me. So, but you guys are all, none of you guys are, I don't think anybody here is a freshman. So you already know that. All right, let's talk a little bit before we dismiss. We'll dismiss early today. We're going to finish, on Monday, we're going to finish chapter 19 on capacitors. And this is, look at this, parallel conducting plates connected to a battery. Yeah, that's what a capacitor is, which is what makes time travel possible, in the movies anyways. And what we find is that the charge load Q, left or right, is proportional to the field strength inside a vacuum-filled capacitor anyways. And it's pretty uniform electric field from left to right in this diagram. And so we're going to be studying those. And what we're going to be doing is studying them as elements of an electric circuit. Right? Now that we've got the basics of electric field and voltage, electrostatic potential, we can start talking about circuits. And I want you to look at something here. The left side plate is marked positive. The left side terminal on the battery is marked positive. The right side terminal on the battery is marked negative. And that's what you're looking under the hood of your car. That's, usually you can make it out if it's not too grimy and dirty. And the right side plate is negative. Now what that means is that everything is equilibrated. All right. This is a state where the plates are fully charged. And charge is not in motion. You're not driving electrons out of the battery and into the right-hand plate. You're not stealing them out of the left-hand plate and pushing them into the battery, drawing them into the battery. It's already done. All right. And this is something that will happen with any battery. At some point, a battery will no longer have the voltage to push any more electrons over to that negative plate and draw out electrons from the left-hand plate. And when that's happened, you can disconnect the capacitor, and what you've got is a stored bit of energy. And if you've ever seen, they make these devices where you shake somebody's hand and you get a little electric shock. It's supposed to be like a little jest that and only like nerdish individuals like physics instructors have those. And they greet each other, hey buddy, and the other guy's got to say, because he's a nerd as well, so he's thinking up in the ozone layer, so he always gets tricked. We go around with these little things, and they zap you, right? And it's a capacitor. But here's another kind of capacitor. This is one that's got some material medium in between. And the thing about the stuff that you put in there, you polarize the material, and that changes the magnetic or the electric field a little bit. All right, and we're going to talk about that. So there's this kind with the vacuum. So this is ideally a vacuum between these plates, and then most capacitors that we have today are filled with a material medium like mylar or paper. Different things, carbon. Different things, and they polarize. Now, you may be thinking to yourself, Dr. B, why are we talking about capacitors? Well, if you've ever seen on TV, like in the emergency room, and somebody's heart stops, right? And they grease up their chest with a little bit of ultrasound gel or conducting gel, and then they put the two paddles on their chest, and they say, clear! And everybody steps back, and then bam, the machine, and that's a capacitor discharging through that guy's heart to get it woke back up. And sometimes they got to do it 2 or 3 times. But that's a capacitor, a defibrillator. And there's capacitors, in your iPhone, there's capacitors all over the place. Little ones. And they're used for various kinds of circuits, oscillating circuits and stuff like that. But so we're going to be talking about that. So your homework over the weekend is to read up to 19.7, so section 5, 6, and 7. I think 7 has talk about defibrillators. It's a short little chapter. And I'll start lecture on Monday with 10 iClicker questions about that. So be ready for bear, and they're not going to be easy questions. All right, you're dismissed. No, I didn't. I was going to, but I forgot.